The Railgun is a weapon developed by the US Navy. The principal operation of the Railgun is based on the electromagnetic phenomenon of Lorentz force, which states that the force experienced by a current depends on the size of the current and the electric and magnetic field surrounding the current. This follows the left-hand rule, which given the direction of the current and an auxiliary magnetic field, tells us the direction of the resulting force experienced by the current. In the Railgun case, the charge flows through the rails and the projectile itself. The external magnetic field experienced by the projectile is in fact the magnetic field produced by the current flowing through the rails. The main way of producing more force for the projectile is by increasing the size of the current flowing through the loop or increasing the rail length. For military applications, the shorter the rails the better, as this reduces the size, weight, and profile of the gun, making it a smaller target. Thus the rail current alone must provide sufficient energy for propulsion. Consequently, the currents used are extremely large, in the order of megaamps. To power the rails, the energy will be drawn from the ship to charge up capacitors before firing. About 33 megajoules of energy is stored before firing. This is equivalent to a 33-ton car traveling at 161 kilometers an hour. The railgun has advantages over the conventional chemical weaponry. As the railgun relies on a huge speed of the solid projectile to deliver kinetic energy upon impact, the solid munitions remove the hazard of storing high explosives on the ship or leaving unexploded ordnance on the battlefield. Also, the weight, space, and cost of carrying solid munitions is less than conventional ammo. The high speed of the projectile of Mach 6 permits the railgun to fire accurately over short distances or over a range of 185 kilometers during the low drop-off of the projectile. This is quite remarkable compared to record distance covered by a conventional naval gun being 33 kilometers, while the longest effective shot distance where an actual target was hit was only 24 kilometers. The downside of the railgun is its power consumption. To produce large currents, the railgun needs 25 megawatts, which is difficult to provide and slows down the firing rate as it takes time to collect needed energy. Currently, the US ships can only provide 9 megawatts. There are new ships being deployed, however, such as Zumwalt-class destroyer, which may house such weapons in the future with its 18 megawatt power supply. Another issue with the railgun is the large currents. As the pulse delivered to the rails is like very high-frequency AC current, the rails are subject to the skin effect, where the current in the conductors concentrate on the outside of the conductor, and the proximity effect, where the rails are inducing eddy currents in each other. These effects increase the rail resistance, which contributes to major heating of the rails, and combined with the friction of the sliding contacts of the projectile create wear and tear issues. The fire you see in these images is in fact the rails being vaporized. This shortens the weapon's longevity and fire rate due to necessary cooling time. A weapon configuration isn't the only possible application of such a system. The development of aircraft launch system called EMALS to be deployed on the new Gerald R. Ford class aircraft carriers is another application. The new launches will be simple in design, thus requiring less maintenance and crew to operate. They will also be gentler on the airframes, as there will be a feedback system and finer control of the launch, which was not possible with the old steam launchers. A similar, albeit hypothetical, application of the railgun is the launching of material into space. This could reduce the cost of space travel significantly to about $530 per kilogram, which is incredibly cheap compared to even the cheapest current cost of $20,000 per kilogram provided by the latest SpaceX cargo spacecraft. Nothing about this technology is unfeasible. It's simply a matter of time, interest, and funding before such applications will be realized. Thank you.